So our second talk tonight is by Jos de Bruijne. He is a staff astronomer at the European Space Agency. That's right, yes. I always get ESO and ESA confused. So Jos has worked with the Gaia satellite since 2002. And one of the cool products that Gaia has produced is a catalogue of the 3D positions and motions of stars, of nearly 2 billion stars in our galaxy. So today he's going to talk a bit about how Gaia actually measures these positions and how watching the positions of stars. So from Ricardo's talk earlier, where the ancient Celts looked at these single positions very roughly of when the star rises in the sky before the sun. Jos is going to talk about the very, very accurate positions of these 2 billion or so stars and how their motions over time can actually tell us a lot about their distances, of the structure of our Milky Way galaxy. So a fun fact about Jos is he's trying to perfect the perfect Lego model of the Gaia satellite that looks like that on the right. So, over to you.
Yeah, thanks, Wendy. Yeah, good evening. My name is Jos. I work for ESA, as Wendy just told you. Actually, I had a challenge tonight because I have like 300 view graphs about the Gaia mission, and tonight I can only show you about 15 or so. So I had to really make a down selection. And actually, I won't be talking much about Gaia itself. I will be more talking about astrometry, and I'll explain in a second what that means. Does it work? Yeah. So first I want to tell you something about this map. This is a map that our spacecraft made, Gaia. And what is very conspicuous in this map is this bright band of light that you see. Is there a pointer here? Maybe I should just point it out. It's the bright band of light that you see along the equator, which is our own Milky Way. And to explain a little bit what that is, let me just go back to a map that you probably recognize. This is just an Earth map with the equator along the horizon, the North and the South Pole as you know it. And this is actually the full surface of a sphere of our Earth. And similarly, as you can depict the surface of a sphere or on a full map, you can do the same for the celestial sphere, for the heavens. So rather than depicting the sphere of the Earth as seen from the outside, the Gaia map is the sphere of the heavens, but seen from the inside, as an observer at the center of the celestial sphere. And what is Gaia all about is about understanding the structure of this band of light that you see there, our own Milky Way. And what you actually see here is the collective light of millions and millions of stars that are all far away and that are not close enough to see individually. So you see the integrated light of all these stars, and that shines as a band of light in the sky. So if I take a picture of a Milky Way lookalike galaxy, you would see something like this. So this is kind of a different galaxy, not our own Milky Way. And what you see here is a few different characteristics of a Milky Way like our own Milky Way. And what you see here is a very thin disk of stars. This is the structure that you see along the diagonal. That's hundreds of billions of stars in that disk. Then you see in the center, there's the nucleus of the galaxy, where typically there is a supermassive black hole of a couple of million up to a few billion solar masses. So it's very, very massive. And then you see the bulge of the galaxy. Also our own galaxy has a bulge. It's this lenticular structure in the center, composed of hundreds of millions of stars. And then what you can't really see in this picture is there's a halo of matter around the galaxy. It's roughly circular or spherical, and most of the matter in that halo is dark. You can't really see it, but you can measure it because it exerts gravity on stars that are moving through the halo. And actually, if you take a picture of another galaxy, but now you look at it from the face, you would see something like this. This is a real galaxy taken by an ESO telescope quite some years ago. And if this were our own galaxy, this is also a Milky Way lookalike. This would be the center of the galaxy, where the bulge is located. And our sun in this representation would be something about in that location, at about 8,000 parsec distance. And a parsec, to remind you, is about 3 light years. So that's the distance that light travels in 3 years. So that's roughly 25,000 light years from the center of our galaxy to And what Gaia is basically about is to unravel the structure, formation, composition, and the evolution of our own galaxy. That's why we built that spacecraft, and that's why we currently operate it in space. That's the real reason to do this. And how do we do it? Well, actually we use stars in our own Milky Way to measure properties and to unravel that history. And why can we use stars? Well, it's simple, because stars, they have something inherited from their birth. And what they inherit from their birth are their motions and their chemical composition. So the way in which these stars are made up, which kind of elements, and how they move through our galaxy, that contains direct clues about where these stars came from and actually where they will be going to in the future, obviously. So Gaia is all about measuring how stars move and what stars are made of. That's basically our tool to unravel the chemical composition of our Milky Way. And I brought you some kind of cartoon of what we think has happened over the past 13 billion years. So since the beginning of the Big Bang, our Milky Way has basically been in a cannibalistic event. It has basically eaten up smaller galaxies that came by, and it has swallowed these and has grown in size over the billions and billions of years. And this is just an artist's view of smaller satellite galaxies that were, well, passing by and eaten up by our own Milky Way. And this has happened hundreds and hundreds of times, and our Milky Way has grown bigger and bigger over the course of the billions of years that it existed. And actually, in this image, this is roughly 15 kiloparsecs, so about 45,000 light years. The center of the galaxy would be again in the center. And what I can show you is what happens if you have one of these smaller galaxies being eaten up by our own galaxy. And this is what happens. This movie, I've now taken away the Milky Way, so that you can just see the captured galaxy. But what you see is that something that was very spatially concentrated and clearly recognizable 3 billion years ago is slowly being eaten up by our own galaxy. And over the course of these 3 billion years that the movie lasts, basically these stars are spread out all over the sky. They are just all over the Milky Way. And from the location where they are today, you can't really recognize that they came from one merger event in the past. But what you can do is, if you can measure the motions of these stars and their chemical composition, you can go back in time and you can still recognize these stars as belonging to that one particular merger event. So by measuring these properties for 1 billion stars in our own Milky Way, and by basically unwinding the clock in our computers, we can unravel the formation history of our Milky Way. And that was of course a cartoon and a simulation, and this is a real image of a galaxy. And what you actually see here are the tidal streams. You see these bright arcs still there, which are direct observational proof of infalling mergers that this galaxy has suffered in the last hundreds of billions of years. So this is not only theory, this is actually happening in the universe as we speak. And our Milky Way, that's the past of our own Milky Way. So now I want to come to the second part of my talk, which is to explain how Gaia does this. So how does Gaia measure these motions, and how easy or how complex is that? Well, I have to go back to the branch of astronomy that is called astrometry. And formally speaking, the definition of astrometry is that it deals with involving the precise measurements of positions and movements of stars and other celestial bodies, so asteroids, etc. And this is an image from the 1970s of quite a frustrated astronomer, I believe. But what he tried to depict is that astrometry stands at the basis of the whole of astronomy. So you have astrometrists who basically carry the whole, let's say, the weight of all the knowledge in astronomy. Above that you have spectroscopists and photometrists, so people who look at the brightness and the chemical composition of stars. And if you don't know where your stars are, how far away they are, you have difficulties in interpreting your measurements, your spectroscopy and your photometric measurements. And then even above that you have theories about atmospheres, interiors of stars, interstellar medium, etc. So to work in that domain, you actually need the spectroscopy, the photometry, and for that you need the astrometry. And actually above that you have a fourth layer, and it says here it's cosmologists, general relativists, cranks, and other fuzzy-brained users. I have no idea what was wrong with that guy, but what we try to depict is that astrometry is really a core essence of understanding the universe. You need to know where stars are and how they move. So now I want to show you something, how this works in practice. And I think I have a simulation which I can show you in a minute, but I think I can actually do a real 3D demo here, but I need some volunteers. So actually I need a couple of stars, and I need one person here to mimic the sun. So is there any volunteer who wants to play the sun? Okay. Yeah, good. You don't have to do anything, just stand here. Roughly here, so that I can walk around you. Okay? Then I need a star I want to measure the distance of. So someone in the second row, doesn't really matter. Please stand up, you're good, yeah, thank you. And then I need, well, just, you can stay where you are. Just act, well, but please stand up. Great, great. And I need some background stars. So in the far row, can you all stand up in the last row? Because I need you as my reference frame. Great. So actually, I call you sun, I call you star, and you are my references. So what I want to do, I'm the Earth, and Gaia is just close to the Earth, and I want to know the distance to my star, which is you. And actually what I'm going to use is I use the fact that I'm not standing still as Earth, but I move around the sun. So when I look at you from this moment in time, I see you projected against the background stars in that direction, actually towards the exit of the building. But now I'm going to move around the sun, and this is of course going to take a real year to move around. And now actually I'm half a year away, because I have moved exactly from that opposite position to this opposite position. And now I look again at you, at my star, and then I see you're no longer close to the exit for me, but you're really in line with the last person of my reference frame. And actually, half a year later, well, I move back, but I come here, and you are there again. And if I continuously look at you while I'm just going around the sun, I see you slowly shifting around compared to the background stars. And actually, if someone on 2 lines further would stand up and I would be observing that star, that person would be doing the same for me. It would also show shifting compared to the background stars. But the shift of my first star, of the young man here, is larger than the shift of this person who would be behind there. And that's purely a perspective effect. And the further the stars are away, the smaller this perspective effect is. And the closer the star is, the larger that perspective effect is. That's a directly inversional relationship. Thanks for your brilliant, all of you. So actually, in an image, this is our sun. I want to know the distance to that star. I have the Earth there, which is 1 astronomical unit away. I look from the Earth to that star and I see it projected towards the top right. And then that angle where I basically want to measure is the parallax angle. That's basically my displacement with respect to the reference star that I would measure if I were at the center of the sun. Well, that obviously I can't measure. But what I can measure if I go around the sun is I can measure twice that angle, twice the parallax angle. Because when I look at the star from this vantage point half a year later at that vantage point, I see that the star has moved that angle of the sky. And actually what Gaia tries to do is it basically tries to measure that angle of the sky continuously for 1 billion stars. So it is observing the night sky for 7 or 8 years at the moment, and is continuously looking at all the stars and measuring these tiny shifts of the sky. And actually, of course, if you would do that continuously, you would actually see that these stars are moving in an ellipse on the sky, which is just a projection of our Earth orbit around the sun. So then, the real challenge is that the galaxy is unimaginably large. And the consequence of that one is really that parallaxes are really infinitesimally small. I could do a second demo, but I won't do it. But just imagine, I could ask for a hair of somebody's in the audience and just take it here. But I won't do it. But imagine I have a hair here of someone. And imagine I would go on my bike and I would cycle out to the edge of town. Imagine how small that hair would want to be if I would be at the edge of town. Then imagine I'm going to cycle further and tomorrow I will be at the edge of the country in Groningen or somewhere else, a few 100 kilometers away. That hair would really, really be tiny if I would stay here as an observer and would try to watch that hair. And now imagine we are looking at a hair which is 350 kilometers away. So that's comparable to from here to London, for instance. So imagine you have Queen Elizabeth at home in Windsor Castle and you have a hair of Queen Elizabeth. And then I'm not talking about the length of a hair, but I'm talking about the thickness of a hair. And imagine that tiny angle seen from here, from this room in Leiden. That corresponds to the parallax of a star at the galactic center. So if you take a star at 25,000 light years away, and that star is doing that little parallax dance over here, that angle on the sky corresponds to about 100 microarcseconds, and that corresponds to the thickness of a hair of Queen Elizabeth when she is in her bedroom in Windsor Castle. And actually, Gaia can do 10 times better than that. So it is really an extraordinary mission which can do extraordinary things. And in the equivalent, let's say, demonstration that you think is you launch an astronaut, he or she goes to the moon, puts a Eurocent coin there, flies back, and then you try to observe that Euro coin cent on the moon, and that corresponds, that angle corresponds to the same, to this 100 microarcseconds. And the real story here is that the galaxy is large and space is large, and there's a lot of nothing between stars. And one of the nice quotes I have from John Updike is that the chief characteristic of the universe is emptiness. There's infinitely more nothing in the universe than anything else. So the distance between stars is huge, and these parallax angles are really, really tiny. So I've brought you a movie to show, let's say, a star field, and I have the moon there for scale. And now I'm going to show you the parallax motions of all these stars. But I had to exaggerate these motions by a factor 10,000 to make them visible. So I'm going to just show it. You see some stars make very tiny ellipses on the sky, some you barely see moving at all, so they are really far away. There's one in the left which is just passing by quite quickly, makes a very large angle on the sky. And you see all the stars have these different parallax circles depending on their distance. And now the second complication is that stars don't stand still in space, they are moving, and stars are moving with respect to our sun. So what happens is that all the stars also are moving on the sky along straight lines or along great circles. And in this particular case, that star is not just standing still and making that parallax motion, it is also moving towards the lower left. And all of these stars in this field have a different motion, some large, some small, some left, some to the right, some up, some down, etc. And if you combine that motion, this is what you get. You get a whole different spectrum of motions, depending on the peculiarities of the star and depending on the distance of the star. And in this particular case, you see some kind of rosette pattern appearing. And this movie lasts about 3.5 years. So you actually will see 3 different loops which correspond to 1 year, one parallax motion. And then that loop is elongated by the proper motion of the star, by the real motion of the star compared to our sun. And what Gaia is doing, it is with minute accuracy or extreme accuracy, it is monitoring all these motions on the sky. And then basically in the last view graph, this is what Gaia in a nutshell is. We measure these paths on the sky, depicted by the red line here. We monitor that path for, well, 1.8 billion stars, so 1,800 million stars. We monitor that path for 5 years. And for each star, we typically observe where it is on the sky about 70 times. And then the only thing we do is we fit for every star a 5-parameter, well, motion and distance model. So the distance is the size of the ellipse. The motion is, well, the extent of the elongation and the direction in which it goes. And we fit that model to retrieve the holy astronomical grail. So that's the reference position, the proper motion, and the parallax. And that ends up in our catalogue, and that is brilliant science. So I don't have time to go into that science. I mean, there's 2,500 papers written with Gaia data so far, and we haven't even had our real data release yet. We have had 2 kind of teaser releases, and the real first data release is coming up on the 1st of June. But it would take a week to explain and to go through all of that. I would be delighted to do so, but not tonight. So thanks for your attention, and let's have one more.
Great, thank you for that. Maybe we should have you back for another short talk on some of the science that can be done. Are there any questions?
that the JWST has a measured angular resolution of like 70 milli-arcsecond, and you were talking about micro-arcseconds. So how does that? And I can't imagine that Gaia has a better resolution than this JWST.
Yeah, so the question is, how come that Gaia does micro-arcsecond astrometry while James Webb does milli-arcsecond, has milli-arcsecond angular resolution? So that's a sharp remark and a good question. The key point is that angular resolution is not what we care about. Well, we do care about it. We have large mirrors and high quality optics, but our angular resolution is similarly limited to about 100 milliarcseconds. The challenge to go to the microarcseconds is that in the end we make these 70 data points and we see that star move in that rosette pattern, and the final uncertainty on the parallax that we fit to that pattern and the motion that we fit is of the order of microarcseconds. So it is not our angular resolution, but it's the uncertainty on the parallax that we estimate from all these measurements that we make. And that can be done very accurately. That was a question there.
Thanks, very interesting. You say that the resolution is about 10 times better than the expected parallax at the start of the center of the Milky Way. So that means that you can measure parallaxes on stars on the other side of the Milky Way, the other half. But can you see them? Can you look through the Milky Way to see those?
Yeah, so the question is, in principle we can measure the parallaxes of stars at the galactic center, and we could in principle even go beyond that, but can we see them? And the answer, that's a very good question. The answer is with large difficulty. And the problem is that our sun and also Gaia, the Earth, is embedded in that disk of the galaxy. And in that disk, it's a very, well, that's the most exciting place of the galaxy to be in, because that's where a lot of star gas and dust is located, where stars are being formed. But that gas and that dust also blocks our view in the optical light, which is what Gaia uses for making its observations. So actually, there's a few what we call windows in the galactic disk, so that's directions on the sky where we can look a little bit further, because by coincidence there's not so much of this blurring gas and dust. But typically we can't look beyond, let's say, 5 or 6 kiloparsec. And we can't even, in the optical wavelengths, you can't look beyond the galactic center. Yeah, for that you need radio wavelengths.
You cannot look at the other side of the center of the Milky Way, but you can look up and down, and there's less dust and gas blocking the view, so you can actually look quite far away. So is it also possible to look at other galaxies?
Yes, so the question is, if you can't look inside the galaxy, but you can look a bit above and below, that's actually what we do. Well, we see the whole sky, so not only the plane of the Milky Way, but also the North, the South Pole, and everything in between. And actually, we do see millions and millions of other galaxies as well. And actually, we have recently set a new reference frame, which is based on quasars. So these are the cores of galaxies in themselves, which are at cosmological distances, and which in principle are standing still. So they are what we call, they define an inertial frame, which is not rotating and not moving. And that's our fundamental reference point that we use to tie our internal catalogue to. And we have millions of these objects in our data set. They're bright enough to be seen.
Are there any galaxies within that limit of 10 times the distance of the Milky Way?
Well, the closest, we have a couple of galaxies which are very nearby. Well, nearby, not on your bike, but we have the Magellanic Clouds in the south of the southern hemisphere, and these are at a distance of about 50,000 parsec, which is 150,000 light years. And then the nearest real galaxy is Andromeda, which is about 700,000 parsec, if I'm not mistaken. And there actually, that's kind of 2 times the full moon on the sky, if you look carefully in the Gaia data. And there we actually see individual stars and bright stars, and we actually see them rotate as well in their own galaxy. So in the Andromeda galaxy, we have tens of thousands of stars that are observed by Gaia. And if you look at their motions, you see that they are rotating in the disk of the galaxy, like our own Milky Way is also rotating. And of course, there's much more galaxies which are just, if you put them further away, they become smaller and smaller, and at some moment you don't see the stars anymore. You just see blurs of light.
How time detailed is the Gaia data? Like, does the telescope do a full sky image every night, or is it like on larger scales than that?
Yeah. So the question is, how long does it take for Gaia to make an image of the sky? Basically, Gaia has quite a big field of view, so it can see about twice the moon when it sees the sky, and then it's just rotating, like it has two eyes. I can't talk when I do the demo, but I will do it now. The two eyes are my two arms, and then it's doing this. So that takes 6 hours. So in 6 hours it makes a full circle on the sky, and the size of the circle is about 2 full moons. And then if you continue that, well, my rotation axis is then slowly processing, so I have to start. I can't do it. Someone else can try. But if you continue that for about 3 months, then you have the whole sky. So typically every 3 months we have a full sky map. And then we just keep on doing that for years and years and years. And then we make these, we find these Rosetta patterns back in the data.
So after like the 5 year when you've got 20 data points on each of your stars?
After 5 years we have 70 data points for every star. That's the nominal number. More questions?
You measure the proper motion of the stars by the parallax. You also measure the velocity away from us by redshift, I guess, because you need 3 components of the velocity. Do you measure the redshift for all the stars, or is it only a subset? Or I can't imagine you measure in the same detail the redshift for all the stars that you have a picture.
Yeah, we get into technical questions now. So the question is, Gaia measures what we call proper motion, so that is purely the motion in the sky, but all the stars also come towards us or move away from us with some velocity. And that's what we call the radial velocity. And that's fairly easy to measure by the fire engine or ambulance siren effect. It's the Doppler effect. So if you just listen to that star, if you observe it in wavelength, you can see that certain features in the spectrum of that star are shifting to the blue or to the red. And then you can directly measure the radial velocity, so the velocity of the star coming towards or away from you. And we do that trick for about 150 million stars of our 1 billion or 1.8 billion. And so it's only a small subset, about 10%. And the reason is to basically have that information, you need to disperse the light. So you have a star of a certain color of light, but then you have to break up the starlight into the different colors in order to use that Doppler effect. And then you introduce noise if you do that, because you spread the light over a certain amount of pixels, and each pixel you need to read, and then you get more noise. So that limits our ability to use that effect for about 150 million stars. So for about 10% we have 3-dimensional velocities. For the remaining stars we have 2-dimensional velocities. That's correct.
Great, thank you very much for that. I think if there are more questions, Jos will be here, so you're welcome to ask him even more technical ones or other questions as well. So thank you very much, Jos.